In this lecture video, we will understand what are the different IoT device design and selection considerations. So in any IoT system, the processor, that is the microcontroller or the microprocessor, controls all the operations of the IoT device, and just like a human brain, it takes inputs, makes decisions and controls the outputs. And it decides how data is collected, processed and stored and then transmitted. That is, the processor will collect the data from the sensors, processes it like calculations and stores it if needed. And it also sends the data to other devices or cloud servers for further use. For example, we have a smart temperature monitoring device where a temperature monitoring system uses a low powered processor because it performs simple tasks, and this will help to save the battery and allows the device to run for a long time. One more example is a smart surveillance camera where it needs a powerful processor in order to handle video processing and real-time analysis, and high performance is required for such tasks like motion detection and image processing. Now we have some popular platforms such as that is the popular development platform such as Arduino and the Raspberry Pi. This Arduino boards are simple, low cost and ideal for basic IoT projects, and these are easy to use. It has a wide community support. These are ideal for simple IoT applications, and also these are the low power microcontrollers, whereas the Raspberry Pi these devices are more powerful and suitable for complex applications, and these can be used for AI and video processing, because these have high performance and these run full operating system like Linux, and it is suitable for complex IoT applications, and it is great for edge computing, multimedia and artificial intelligence. So here the suitability, it depends upon the performance requirements, power consumption, then connectivity, data storage, security and cost constraints. Now the first consideration is the size, that is nothing but the form factor. So here the size determines where and how the IoT device can be used. That is, the physical size of an IoT device affects its placement and application. And small devices can be used in wearables or tight spaces, while larger devices are suitable for industrial or outdoor environments. And smaller size, it means it is a portable, wearable and it is energy efficient. That is, smaller IoT devices are easy to carry and can be worn on the body like smartwatches or fitness bands, and they consume less power, making them suitable for battery operated and long duration applications. And the larger size means more components will be there, but high power consumption will be there because of the more components. It means that larger devices can include more sensors, processors and communication modules for advanced functionality. However, they require more energy to operate, making them less efficient for portable use. So some examples, real-time examples are smartwatches. These need tiny processors because the space is very limited here, and these are very small, wearable, low power. Second is smart agriculture soil sensors, where small nodes are placed in the hundreds across the fields, and here these are also small in size and these are discrete and energy efficient. And one more is industrial monitor panels, where larger size is acceptable, and here more components will be there and power consumption will be more. So here now actually the size should be small. Now, can you wear a large computer on your wrist? No. So because of that only, the size is one of the important and critical consideration to design the IoT device. So here obviously you you don't want or you cannot wear a large computer on your wrist. Hence miniaturization is essential, because of which the wearable devices have come into existence. Second consideration is the energy consumption, where it determines the battery life and sustainability. Energy consumption decides how long an IoT device can run on battery. Lower usage means longer battery life and more sustainable operation. And low power processors are very crucial for the remote IoT devices. That is, the devices placed in remote areas like forest or farms. These cannot be charged frequently. So low power processors are used to ensure they work for months or years without maintenance. Some real-time examples are the forest fire detection sensors, where batteries must last for months. That is, these sensors are deployed in the forest where power supply is not available, and they must run on the batteries for long durations. So efficient, that is the energy efficient design is very essential here. Second is the smart door sensors, which run for years on small batteries. So the door sensors which are used in homes, those operate on small batteries, and these are expected to last for years, and they consume power only when triggered. That is making them highly energy efficient. And third example is CCTV cameras, which need more power due to continuous processing. And these CCTV cameras continuously record and process the video data. So this requires more power. So they are usually connected to a constant power source. Now, suppose you have a mobile phone battery and you have a desktop computer power supply. Now, if you compare these two, a mobile phone is designed to save the battery and run efficiently for hours, and a desktop here, it consumes more power but provides high performance continuously. Next consideration is the cost. The cost affects how many devices can be deployed. That is, the price of each IoT device, it directly impacts how many units can be installed. And higher cost limits deployment, while lower cost allows wider coverage and the usage. And here the lower cost, it means that the adoption is wider and scalability is also more. So affordable devices make it easier for schools, industries and farmers to adopt IoT solutions, and it also helps in scaling the system by deploying more sensors over larger areas. Some real-time examples are the smart classrooms, where multiple temperature sensors are needed, which are cheaper hardware and are preferred. So here many sensors like temperature, humidity, then carbon dioxide, these are needed across the classrooms. Using low-cost devices makes it possible to install sensors in every room. Then one more, you have gas leak detection systems, which is used in industries. Here the industries install many sensors only if it is affordable. These industries require multiple sensors for safety across the larger areas, and they prefer cost-effective sensors so that more units can be installed for better protection. Now, one example scenario you can consider here: if one sensor costs 5,000 to deploy 10 units, that is, if each sensor is expensive, only a limited number, that is 10 units, can be deployed. And this results in less coverage and few monitoring points. Now suppose if one sensor costs 500, so we can deploy how many units? We can deploy 100 units. That is, if the sensors are affordable, then many more units can be installed, and this will improve the monitoring accuracy and the system effectiveness. So lower cost, more devices, more coverage area, and also higher impact. Next is the memory. So here the memory determines the data storage. That is, memory stores the data collected from the sensors for short-term or long-term use, and this helps in analyzing the past data and making better decisions. Then comes the local processing capability, where the memory allows the device to process the data locally without sending everything to the cloud. And more memory means the device can handle more complex tasks on its own. And also this memory determines filtering and the buffering, where memory temporarily stores incoming data before processing or transmission, and it will help in filtering unnecessary data and sending only important information. Now the types of the memory are RAM, and which is the temporary processing, which is used for temporary processing, and RAM is used for temporary storage while the device is running, and it stores the data, instructions data and instructions which are needed for immediate processing. Okay, so it is a volatile memory and data is lost when power is off. Next is flash or EEPROM, which is a permanent storage. So here it is a non-volatile memory and the data is retained when even without power. So here the flash or the EEPROM stores the data permanently even when the power is off, and it is used to store the programs, settings and important records. Some real-time examples are the vehicle tracking, which stores the GPS logs, and here the GPS data is stored temporarily in the memory before being sent to the server, and this helps in tracking the location even if the network connectivity is lost. Second is the health monitoring, which stores the patient's readings locally. So here the devices store the patient's readings like heart rate, temperature locally, and then this ensures no data is lost before it is transmitted to the doctors or the cloud system. So here the data is saved even when the device is offline. And one more example is the smart cameras, which need high memory for images or videos. So here the cameras require a large memory to store the images and video data, and higher memory helps in smooth recording and real-time video processing. So suppose students are asked to compare the calculator memory and the smartphone memory. So here the calculator memory, it is very small memory and it can perform only simple calculations, whereas the smartphone memory, it has a large memory allowing it to store the apps, photos, then videos and perform the complex task. Next is the processing power. So here it determines the speed and the complexity of the operations. That is, the processing power will determine how fast a device can perform tasks and how complex those tasks can be. Higher processing power is needed for advanced operations like artificial intelligence, then image processing and real-time decision making. And here it is needed for artificial intelligence, video analytics or complex computations. So the applications like artificial intelligence and video analysis, these require handling large amounts of data quickly, and because of which powerful processors are required to process the data efficiently and give real-time results. And here some real-time examples are the temperature sensor. Then you have a temperature sensor, which is a which has a low processing power, and it is sufficient for that, and it reads the temperature and it sends the data. And here low processing power is sufficient for its operation. Self-driving cars where extremely high processing power is required, and these cars analyze the camera feeds, sensors and surroundings in the real time, and they require extremely high processing power for safety and quick decision making. And the third is the face recognition systems, which need powerful processors, where these systems process images and identify faces using the algorithms, and they need powerful processors to ensure accuracy and the fast response. So here high processing power enables the smarter, faster and more accurate IoT applications, but it may also increase the cost and the energy consumption. So here you can see these applications where you have a smoke detector. Processing required is very less here. Example is it detects smoke and triggers the alarm. Then one more is smart home hub, where the processing is medium and it handles multiple devices, automation and voice commands. And the third is the video surveillance AI, where the processing required is very high, and examples are the real-time video analytics, then object detection and other alerts. Sixth is the input-output rating, that is the input-output capability, and here the IO rating defines how many sensors are actually sensors and actuators can be connected to an IoT device. The more number of IO pins, more IO pins, input-output pins, allow the device to handle multiple inputs and outputs simultaneously, and each sensor or actuator needs a connection pin on the processor, and if a device has limited input output pins, it can only connect to a few sensors. So here uh, here you require more number of inputs, then you will be having more number of output pins also, that is, you will require more number of output pins also. So here one more thing is the voltage capability. Okay, voltage capability matters here because different sensors and processors may operate at different voltage levels, and matching voltage is important to avoid the damage and ensure proper communication. Some real-time examples are the industrial automation, where multiple sensors requires many input and output pins. That is, factories use many sensors such as temperature sensor, pressure, or motion sensors, and so the controllers with high input-output capability are needed in order to connect all the devices. Second example is the traffic monitoring system, which needs cameras as well as the environmental sensors, and the system include cameras, then pollution sensors and the speed detectors, and this requires multiple input output connections in order to handle different data sources. And the third is smart irrigation system, where you require the soil moisture along with the humidity and the temperature sensors. So it uses the soil moisture, humidity and the temperature sensors all together, and hence sufficient input output pins are needed in order to connect all the sensors. So here you can see you have a processor here. Now for a temperature sensor you need some pin, humidity sensor you need some other pin, and for soil moisture you need soil moisture sensor you need some other pin. So more number of pins, input and output pins must be available. Now one practical example here is, suppose you have an old sensor which use the 5 volt, and the modern processors, these use 3.3 volts. Now these need voltage converters, which will increase the circuit complexity and the cost. So older sensors work at only 5 volt, while the modern processors work or use 3.3 volts. Now in order to connect them, these voltage converters are required. Okay, voltage converters are required in order to required, which will increase the cost and the complexity. So more IO pins, more devices can be connected, and if there is any voltage mismatch, it needs extra components, and proper selection is efficient and safe for the system design. And next is the add-ons, that is built-in features. So here add-ons are extra features already included inside a device or a processor, and they reduce the need for external components, making the system simpler and faster to develop. And here the integrated features will reduce the development time and the complexity. That is, when features like Wi-Fi or analog to digital converter are already built in, you don't need to connect extra modules. This will save the time and reduces wirings and lowers the chances of the errors. Some common add-ons are the A to D, that is analog to digital converter, where which converts the analog signals like temperature or light into digital data, and this will allow the processor to understand the process, to understand and process the real world signals. Then you have Wi-Fi or Bluetooth. Here this will enable the wireless communication between the devices and the internet, and they are essential for remote monitoring and control. Third is the USB or the Ethernet, which is used for wired communication and the data transfer, and it is helpful for connecting the devices to computers or networks. Then comes the real-time clock, where it keeps a track of time even when the device is powered off. Useful, that is, it is useful for time-based operations like scheduling and the logging. And next is the wireless communication modules, where it includes technologies like Zigbee, LoRa, etc., and they help devices communicate over short or long distances. Some real-time examples are the smart home devices, where it will be having the built-in Wi-Fi, which allows the direct connection to the internet without extra modules. Then you have environmental monitoring, in which you will be having built-in analog to digital converter, which will read the analog signals from the sensors like temperature, humidity, and pressure. And one more is the logistic tracking, where it is a combination of the GPS and the wireless communication on board, where the devices with GPS and the wireless modules can track the location in real time, and the data is directly sent to the servers without extra hardware. So suppose you buy a laptop with Wi-Fi built in, and one more, you have an external USB Wi-Fi adapter. Now buying a laptop with built-in Wi-Fi is easier and the cleaner. Okay, and using an extra USB Wi-Fi adapter adds extra cost, space, and complexity. So these are the considerations. These are the selection considerations which are used to design the IoT device. That is, you are having first one was, I think, size. Then you are having processing power. You have memory. Then you have energy consumption, add-ons, input output ratings or input output pins. So this was about the IoT device design and selection considerations.